We continue with complex integration as we now focus on complex differentiability. Okay, so the introduction to here is in real calculus, right? Differentiation measures how a function changes along a line. So, but in complex analysis, a function is defined on a complex plane, which is signified by z equals x plus iy. This means differentiation must work consistently in all directions, not just left or right. So if you're differentiating, it must work along x-axis and along the y-axis because every complex expression has both a real and imaginary component, the real on the x and the imaginary on the y-axis, like that. So it must work along all lines. So this makes complex differentiability much stricter than real differentiability, just like what we saw for limit and continuity. It must happen along all the paths. Then we talk about definition of complex derivative. So the derivative of a complex function f of z at a point z naught is defined as f prime z naught equals f prime of z naught rather equals limit as h approaches zero of f of z naught plus h minus f of z naught all over h, where h is a complex constant. And it is important to know that the limit must exist. That was why we had to talk about limit and continuity before we came here. So the limit must exist. And for the limit to exist, it means that the limit along all paths, along x-axis, along y-axis, that is when x is 0, when y is 0, and probably when x is equal to y, and maybe y equals x squared, and things like that, must all exist for all possible paths. The limits must exist. So the limits must be the same regardless of how h approaches 0. So that's part of what I've said. So this includes all directions in the complex plane. So that's the simple definition of complex derivative. Although it is stricter and trickier because you have to consider many paths. So then we talk about direction interpretation. In real calculus, h approaches zero only along the real axis. But in complex calculus, h can approach zero from infinitely many directions, whether the real axis, the imaginary axis, the diagonal paths, and some arbitrary curves. So for the derivative to exist, all these approaches must give the same limit. All right. And that was why the last video was really important. So we talk about real and imaginary components now. So let the function be written as f of z equals, normally we are used to f of z equals x plus iy. But what if that x and y now are now they are now functions of other variables. For instance, f of z is equal to u of x comma y plus y of I of v is also v now is a function of x comma y, where u of x comma y is the real part and v of x comma y is the imaginary part. Of course, we know the imaginary part by virtue of where I is put. So this I shows the imaginary part. So this allows us to analyze complex functions using real variables. So if you express it this way, rather than just x plus iy. So then we talk about the Cauchy-Riemann equations. Of course, we're going to have a video dedicated to only this concept strictly. I guess the next video, so I'm not too sure which one. So f of z is u x comma y, I is v x comma y. According to Cauchy-Riemann, for the Cauchy-Riemann equations, if f of z is a complex variable, then the following must hold. The partial derivative of u with respect to x must be equal to the partial derivative of v with respect to y. This same u and v you have here, right? On the other hand, the partial derivative of u with respect to y must be equal to the negative of the partial derivative of v with respect to x. So partial u partial x equals partial v partial y, while partial u partial y is equal to minus partial v partial x. These are called the Cauchy-Riemann equations. Additionally, the partial derivatives must be continuous. So in the video where we talk about Cauchy-Riemann equations, you'll understand how we derive the expressions. So now, why is complex differentiability stricter? That's the question we need to answer next. So for real differentiability, right, only one direction, which is along the real line. But in that case, there are fewer constraints. But for complex differentiability, there are infinite directions, all right, and it requires directional consistency, and it must satisfy the Cauchy-Riemann equations. Therefore, many functions that are differentiable in the real sense are not complex differentiable. So many functions that you may be able to differentiate, like maybe if you say f of x equals something, is differentiable. By the time it becomes a function of a complex function, you can no longer differentiate that. So let's look at example one. So example one says we have f of z equals z squared, and we want to we want to compute the derivative, that is f of z plus h minus f of z all over h. Of course, that will be z plus h squared minus z squared, because we are given z, right? So f of z plus h means wherever you find z, you put z plus h. So you have z plus h squared minus z squared all over h. So if you expand that, you have z squared plus 2z. That's expand this now. That's z squared plus 2zh plus h squared minus z squared. Z squared cancels z squared. So you have 2zh plus h squared all over h. You can divide through by h because h is common here. So you have 2z plus h. If you now take the limit, because differentiability depends on limit. So f prime of z now is the limit of 2z plus h as h approaches 0. So if you put 0 for h just to get 2z, and that makes sense even in the real sense. If you have x squared, differentiate x squared, you get 2x. So if you differentiate z squared, you get 2z. So this limit is independent of direction the way it is. Therefore, f of z is z squared is complex differentiable everywhere. So it is complex differentiable everywhere because I mean it's a polynomial kind of thing. So let's see in this other case now, we have f of z to be z bar, that's the conjugate of z. So we know z is already x plus iy. So the conjugate of z is x minus iy. So if you approach along the real direction, that's if you focus on change on x, right? So you have that f of z plus h minus f of z over h is equal to 1, right? That is, if you find the limit of this expression as x approaches as along the real direction, that's as y approaches 0, you are going to get we are differentiating. Do I have to write this out? Let me see. Mm, okay, well, in a sense, I mean, I'm going to take some examples at the end of this. So if you differentiate x, you get 1, and this is gone. So you have 1. But if you differentiate y here, you get minus 1. So moving along the imaginary direction now. So where x is 0, so you have negative of this. So since the limits differ, so you have 1 for 1, and the other one is not equal to, and the other one is minus 1. Okay? So as a result of that, so it's more like just taking a limit of this expression. So if when x is 0, yeah. So it's like differentiating directly, that helps too. So the derivative does not exist because the value for one is 1, the other one is minus 2 along different paths. Therefore, f of z is equal to z bar is not complex differentiable. So it simply means that the conjugate of z is not complex differentiable. That's what we're saying. So and we can see all of that here. So if you test that out, you import numpy as np, define the function as conjugate of z, and you define z naught as 1 plus 1j, and you have h values as very small values like this: 10 raised per minus 5, 10 raised per minus 6, 10 raised per minus 7. And if you do all that, and you check all the directions for the real direction, you see the values are going towards 1, 1.00, 0.99, 1.00. So basically 1, but the imaginary direction is always going to towards negative. That's minus 1.000, minus 0.999, minus 1 point that. So real direction goes towards 1, imaginary direction goes toward minus 1. As a result of that, because that limit doesn't though they exist but they are not equal, you can say that the conjugate of a complex of complex number z is not complex differentiable, which is not differentiable basically. So how do we interpret the results? So the real direction is approximately, in the real direction, you have the derivative to be approximately 1. In the imaginary direction, it is approximately minus 1. Okay. And since the limits differ, the derivative does not exist. This confirms that f of z is equal to z bar is not complex differentiable, z bar being the conjugate of the complex number z. So we have a summary table here. So the property, if you talk about the domain, for real differentiability, the domain is the real line. For complex differentiability, it's a complex plane because you have the x-axis, which is real, and the y-axis, which is imaginary. So you have a plane because it's two-dimensional in that case. Then talking about the directions, differentiability is in one direction. For complex differentiability is in infinite directions. Then for the condition, right? The condition for differentiability is that the limit exists. Once the limit of a function exists as the independent variable is approaching a particular value, then it means the function is differentiable at that particular point. Then for complex differentiability, the same limit in all directions. So you must have the same limit in all the possible, all the infinite directions. That makes it more serious. Then the extra requirement for real differentiability, there's no extra requirement. But for complex differentiability, there's the extra requirement that the function must obey the Cauchy-Riemann equations. Then strictness now. Real differentiability is very strict, while complex differentiability is highly restrictive because you have to consider infinite directions. So the final insight we get here is that complex differentiability is a very strong condition. Uh, so functions that satisfy it are called holomorphic functions. So a function that is complex differentiable is said to be holomorphic, and they have highly structured behavior and preserves angles locally. This rigidity is what makes complex analysis powerful. So this rigidity can help to preserve some things. So let's look at some practice problems. So solve the following problems for each function. Determine whether it is function complex differentiable. If yes, find the derivative. That's find f prime of z. If no, explain why. E.g., Cauchy-Riemann equations fail or directional limits differ. So you have questions 1 to 10 as usual. You want to try your hands on them, and you have questions 11 to 20. So I'm going to answer questions 8 and 20. So this is question 8 here. We want to see if f of z equals x squared minus y squared plus I 2xy is complex differentiable. And if it is complex differentiable, then we will look for the derivative. Then for 20, we have f of z equals z squared plus 1 all over z minus 1. For z not equal to z all over z squared plus 1 over z minus I, rather, where z must not be equal to I. Because if z is I, then this function breaks down. It is undefined in that case. So yeah, let's go to the worksheet to take care of questions 8 and 20. Questions 8 and 20. For question 8 now, okay, let me go for problem 8. Problem 8, we are given f of z equals x squared minus y squared plus I 2xy. All right. So the first step we need to take, so step 1, we need to identify u of x comma y and v of x comma y. So in this case, since you are given the function in terms of x and y on both sides like that, so it's looking like this is u of x comma y and this is v of x comma y. If that is the case, then what do? We have u of x comma y to be x squared minus y squared, whereas v of x comma y is 2xy. That's the complex part. So we then we can take partial derivatives. So partial u, partial x, that's differentiate this with respect to x, we get 2x. Then partial u, partial y is minus 2y. And then we have partial v, partial x is equal to 2y. And then partial v, partial y is equal to 2x. Now the question is, so we now check Cauchy-Riemann equations. So check Cauchy-Riemann equations. Check Cauchy-Riemann equations. So if you are given in this form, so you can check Cauchy-Riemann equations. So partial u, partial x is partial v, partial y. Is that correct? Partial u, partial x is 2x. Partial v, partial y is also 2x. Correct. So that's 2x. So that's fine. So the second condition is that partial u, partial y is equal to minus partial v, partial x. So that means, so first of all, what is partial u, partial y? Partial u, partial y is minus 2y. Okay? That's, so maybe I should start from here. This is actually minus 2y, and that is equal to, you know, and what is partial v, partial x? Partial v, partial x is 2y. So that means this is minus 2y also. So this is minus 2y. Du dy is minus 2y. So the conclusion is that, okay, I think I stopped following the steps. I was just going on. It's okay. So the next thing is both equations are satisfied. Both Cauchy-Riemann equations are satisfied. Both CREs are satisfied. CREs being Cauchy-Riemann equations. Both Cauchy-Riemann equations are satisfied. So the function, the function is complex. The function is complex, differentiable everywhere. It is complex, differentiable everywhere. It is complex, differentiable everywhere. So if that is the case, we need to compute the derivative. So to compute the derivative, don't forget we have f of z to be x squared minus y squared plus I 2xy. So that means that f prime of z would have to be uh would have to be partial u partial x plus I partial v partial x. So partial u partial x is, so this is u, this is v. So that is what now? Partial u partial x is basically 2x plus I into 2y. So at the end of the day, that is actually 2 into x plus iy. And this is z, right? This is 2z. X plus iy is z. So this is 2z. On the other hand, if we want to do for y, right? On the other hand, we could say uh partial partial u partial y plus I partial v partial y. So that is minus 2y plus dv with respect to y, right? That's I 2x. Okay, now this is inconsistent, so we can leave it like this. So this is 2z. Well, interestingly, you'll discover that even this expression or this even this expression itself is actually z squared. If you look at it well, this is actually z squared because if you differentiate z squared, you get 2z. We did that before, but except that this one is not written directly like that. So this is 2z. So yeah, and we know that originally, right? Originally, okay, f of z, which is x squared minus y squared plus I into 2xy, is actually the same thing as z squared, okay? The same thing as z squared. How are we sure? You have z squared. This is z squared to be x plus iy all squared. So if that is the case, that means you have x squared, okay, plus 2x squared plus 2x iy plus I squared y squared. So that means you have x squared plus I 2xy. Y squared is minus, so minus y squared. So that means you have x squared minus y squared plus I 2xy. Okay? So at the end of the day, this is basically z squared. And you know that the z is basically 2z. And so we have that on both sides. So the function, so we have all of that going. So that's question 8 right there. So let's go for question 20. Question 20, problem 20 now. So for problem 20, so we are given f of z, which is z squared plus 1 all over z minus I. Be careful, 1 and I are different, so because it can easily be confusing, especially if you're under pressure. So the first step, we need to identify. So first identify function type. So what type of function do we have? So we can see this is a rational function. A rational function is the ratio of two expressions, right? So this is a rational function of z. This is a rational function of z. All right. So the numerator, so the numerator is polynomial in z, and then denominator is also a polynomial in z. Denominator is a polynomial in z. I mean, that's clear, right? That's obvious. This is a polynomial in Z. This is also a polynomial in Z. That's what we are saying. So we have a rational function like that. So the next thing is to check the differentiability. So uh, we see that rational functions are complex differentiable, are complex differentiable, differentiable everywhere, but there are points of discontinuity. Rational functions are complex differentiable everywhere except where where the denominator is zero. Except where the denominator is zero. Okay? So what's the denominator here? Z minus I. So, and that's why this condition is very necessary for the function to hold. So, um, so the denominator Z minus I equals zero. Wherever it is zero, that implies Z equals I. So when Z is equal to I, the function ceases to exist. So we say, so the function both ceases to exist and it is also not differentiable. So the function is differentiable. So the function is differentiable for all Z that is not equal to I. So for any Z that is not equal to I, the function is differentiable. That's the essence of that. So the next thing now is to compute derivative. So to compute derivative. Well, using quotient rule, because we have a rational function, using quotient rule. So because that's a quotient, right? Using quotient rule. So what do? We have f of z. Quotient rule tells us that f of z equals g of z all over h of z. And for quotient rule, that means that f prime of z is equal to g prime of z, h of z minus g of z, h prime of z all over h of z all squared. That's basically what quotient rule is about. So now if we bring back our function, f of z equals z squared plus 1 all over z minus I. So what do we get? So that means that f prime of z now will be uh, g prime of z. Differentiate this z squared plus 1. That is 2z basically into h of z. H of z is z minus I. Then minus g of z. This is h of z and this is g of z, right? So this is g prime of z. Oh, I think I've done something wrong. Yeah. Oh, okay, okay. I think I've switched it. That switching was going to cause a problem. So this is g of z and this is h of z. Great. So g prime of z, right? That is z, that'll be 2z into h of z. That is z minus I minus um g of z, which is z squared plus 1. Derivative of h of z, that is 1, because if you differentiate z minus 1, you get 1. All over h of z squared, that's z minus I all squared. Okay, so we can then tidy things up here. So we have 2, so we can expand. We have 2z squared minus 2z I, that's I 2z, minus z squared minus 1. All right, looking at this, all over, when we expand, okay, I think we can still leave the z minus I squared like that. So we have z minus I squared. So we keep going. So 2z squared minus z squared is z squared here. All right, minus I 2z minus 1 all over z minus I all squared. Of course, for z not equal to I. So that's the derivative we get. That's f prime of z at the end of the day. So we can conclude, so f of z is complex differentiable, is complex differentiable, is complex differentiable for all z not equal to I. Okay, so that's the idea. So you so we can so Z equals I is what you can call the singularity. So we're going to talk about poles and singularity and all of these things as we move on, especially when we get to uh, complex integration or something like that. So yeah, watch out for that. So with this, we come to the end of this interesting video about complex differentiability. Don't forget to try your hands on the practice problems. Uh, determine whether it's complex differentiable, and if yes, find f prime of z. So you have the first 10 questions right here. Okay, I've done question 8 already, and you have the last 10, 11 to 20. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you haven't subscribed, the question is, what exactly are you waiting for? Why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, and that gives you some special privileges, like get to see some videos first, or seeing some videos exclusively because you're a member of the channel, or videos that others don't get to see. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.